Okay, so today's goal is to do some applications of the Poisson distribution, and that's what I will be doing. Okay, so here we have a problem. It says over the course of 365 days, 1 million radioactive atoms of cesium-137 decayed to 977,287 radioactive atoms. Use the Poisson distribution to estimate the probability that on a given day, 50 radioactive atoms decayed. Okay, so we have to figure out what lambda is. Remember, the Poisson distribution, P of X, or P of K, I should say. Oops. Equals e to the minus lambda, lambda to the K over K factorial. Okay, so now we started off with how many atoms disappeared? Well, 10 to the 6th minus 977, 287 atoms decayed in that year. So lambda is the average in the year. So lambda is 10 to the 6th minus 977,287 over 365. And plugging into the calculator, you'll get 62.227 atoms decayed on the average per day. Okay, so per day. Okay, so now what are we interested in computing? We want to know the probability that 50 atoms decayed. X is the number of atoms which decay per day. So the probability of X equals 50 atoms decaying per day is given by E to the minus 62.227 times 62.227 to the 50th power divided by 50 factorial. And this turns out to be 0.0155. That will give you the answer. Okay, so that is problem 1. So here's problem 2. In the last 100 years, there have been 93 earthquakes measuring 6.0 on the Richter scale. What's the probability of having 3 earthquakes in the same year that all measure 6.0 or more? Okay, so we have to figure out what lambda is. So what are we asking, by the way? We want the probability that x is equal to 3. We have to figure out what lambda is. Well, what's lambda? Lambda is going to be, there are 93, and this is in the same year, 93 earthquakes in 100 years. So we want to get the average number of earthquakes per year. So 93 over 100 gives you the average number of earthquakes per year. So this is the average number per year. And we need to use that because we want to know about the same year. And so we want to know the probability x is greater than 3. So that would be e to the minus 0.93 times 0.93 to the 3rd power over 3 factorial, giving us a value, if you plug it into your calculator, 0.0529. So that's the answer to problem 2. Okay, so problem 3. Suppose the probability of suffering a fever from the flu vaccine is 0.005. If 1,000 people are given the vaccine, use the Poisson distribution to approximate the probability that in part A, 1 person suffers a fever as a result, and B, more than 6 people suffer a fever as a result. So the solution here is we need to compute what lambda is. So now let's see. If 1,000 people are given the vaccine and the probability of suffering a fever is 0.005, then if we take the product, we get 5, I believe. And this is the average number of people, the 1,000 people who are going to be suffering. Okay, so now we want to calculate the probability that x is a Poisson random variable with this type, with lambda equals 5, that x equals 1. So what do you get? You're going to get e to the minus 5th power times 5 to the 1st power over 5 factorial, and that's going to be 0.0337. So that is the answer to part A. And the answer to part B is more than 6. How do you calculate the probability that x is more than 6? We calculate the complementary probability. That's 1 minus the probability that x is less than or equal to 6. And that's 1 minus the quantity, the probability that x equals 0 plus x equals 1 plus x equals 2, etc. So, So what is that? The probability x equals 0 plus the probability that x equals 1 plus the probability of x equals 2 plus the probability of x equals 3 plus the probability that x equals 4, etc. So there's a lot of calculation in this one, plus the probability that x equals 5, plus the probability that x equals 6. Now there are calculators which will actually compute online, that will actually do these computations for you. So let me just tell you the answer in this case to this part of the problem. The answer in this case is going to be what? It's going to be, I believe, okay, so I went and computed separately the sum in the parentheses, and I subtracted it from 1, and I got 0.2378. So that's the answer to part B. Okay, so in the last problem I'm going to cover today, it says telephone calls enter a college switchboard on the average of 2 every 3 minutes. What's the probability of 5 or more calls arriving in a 9-minute period? Okay, so what are we looking at here? 2 calls every 3 minutes, but we're interested in a 9-minute period. Okay, so what's lambda? Lambda is going to be, well, 2 calls per 3 minutes, but we're over a 9-minute period. So over a 9-minute period, you got to multiply by 9, giving 18/3 or 6. So lambda is 6. And then what we have to do is compute the probability that 5 or more calls are coming in. Now, the easiest way to do this, or pretty much the only way for us to do this, is take the complementary probability, that 1 minus the probability that x is strictly less than 5, which is 1 minus the probability that x is less than or equal to 4. Okay, which is given by 1 minus the probability that, let me use the PMF notation, P of 0 plus P of 1 plus P of 2 plus P of 3 plus P of 4 And this one I'll write out. It's 1 minus e to the minus sixth. E to the minus 6 will be a factor of all these numbers here appearing in the parentheses, and then it'll be 6 to the 0 over 0 factorial, plus 6 to the 1 over 1 factorial, plus 6 to the 2 over 2 factorial, plus 6 to the 3 over 3 factorial, plus 6 to the 4th over 4 factorial. And this can all be computed on your calculator, as well as you can do it as well as I do, and you get 0.715 as the actual answer. So that is problem 4, and that's the last problem I wish to do today.